Many of the costliest catastrophes in history weren't single events. Take the 2011 Fukushima disaster. It began with an earthquake, which triggered a tsunami and ended in a nuclear crisis. Or the way cyclones bring storm surge, flooding, and infrastructure failures all at once, as with Hurricane Katrina in 2005 and Hurricane Harvey in 2017. Many variants of such super catastrophes exist. The 2011 Thailand floods, for example, destroyed key industrial parts, disrupting supply chains worldwide for computer parts. And of course, COVID-19 caused a global supply chain breakdown, widespread business interruption, and a deep economic recession. These are called compound catastrophes. Disasters that interact, amplify each other, and create domino effects. Traditional catastrophe models usually treat risks separately, one for earthquakes, one for floods, one for storms. But in the real world, risks don't happen in isolation. Events overlap, hazards interact, and their impacts cascade. These compound events or compound catastrophes take many forms. It can be a combination of unrelated events, known as a perfect storm effect, such as earthquake shaking being amplified by strong winds. Then there are domino effects, like explosions, fires, and toxic spills at critical infrastructures. Then we have common drivers such as global warming, which can alter the intensity and frequency of multiple perils at once, for example droughts, heat waves, wildfires. Finally, we have system feedback loops, a good illustration being the one of an outbreak escalating to an epidemic, then to a pandemic. And of course, we may have combinations of all these processes. These mechanisms are well known in theory, yet most research has only examined isolated cases. That makes it difficult to see the full picture while keeping models practical. What we need now is to encode these processes into the next generation of catastrophe risk models. That's why the generic multi-risk platform, or GenMR, was created 12 years ago. GenMR simulates compound catastrophes from the ground up literally. We build a digital template that is a virtual region with layers of soil, land use, water, and cities where catastrophes emerge. GenMR started as an academic exercise, first defining interaction types and exploring how risks amplified. Later, we tested cascading earthquakes and associated vulnerability amplification, as well as the complexity of hydrodam overtopping and failure. Over time, dozens of peril types were defined from first physical principles across the natural, technological, and socio-economic systems. This work led to the CAT Risk Modeling Sandbox, an online resource released with the Cambridge University Press textbook called Introduction to Catastrophe Risk Modeling. But the sandbox currently includes models of only 10 individual perils without interactions. So the next step is to merge GenMR with this peril library, expand it with more hazards, especially climatic and socio-economic ones, and model their interactions at the regional scale. This project will be led by myself, Arnaud Mignan of Mignan Risk Analytics GmbH, together with Professor José Matos of the University of Lisbon, who will focus on local scale hydrodam risk. Our goal with GenMR is simple. It must become a laboratory for catastrophes where we can use reasoned imagination to explore scenarios which are rare, extreme, and which may have yet to occur. This project will help us understand how risks build up and cascade, explore a broad range of hazards across the natural, technological, and socio-economic system, capture the influence of drivers such as climate change or aging infrastructure, and make everything open source with a dedicated GitHub repository and tutorials. By the end, we aim to answer some fundamental questions. What patterns of events lead to the biggest losses, and what critical factors amplify those risks? With GenMR, We are not just building another model, we are building a transparent, comprehensive platform to study compound catastrophes systematically. Our vision is to give scientists, practitioners, and decision makers a new way to anticipate the unexpected and ultimately to make societies more resilient. We are deeply grateful to the SCOR Foundation for Science for supporting this project.